Okay. Hello everyone. So we are welcoming Jean-Michel Redouté from Belgium, and he will talk about smile on camera.
Yeah, SPAD camera.
Smart camera. So I will let you the floor.
Okay.
Very smart introduction.
Okay, excellent.
So
Okay,
the prize is-
Okay, merci. Thank you. Donc, in English, okay, for the streaming, right? Okay. Bon, Smile, you're on SPAD camera. First, I wanted to say, I'll talk 3 minutes in French and then I'll do in English because you'll see. First, I wanted to say, il était une fois des SPAD, and then, I thought, oh, il vient de Belgique, voilà. Il était des SPAD une fois, et haha, et tout. Voilà. Mais ne faites plus la faute. Pourquoi est-ce qu'on dit les Belges disent une fois? Parce que il était une fois Blanche-Neige. En néerlandais, en allemand, on dit er was eens ou er war einmal Sneeuwwitje, enfin Blanche-Neige. Donc là, eens, c'est un adverbe numérique et ça se traduit par une fois. Maintenant, quand un Bruxellois, typiquement, parce que les Wallons, par exemple, ne disent pas une fois, enfin, quand ils veulent dire une fois, ils disent une fois, mais vous voyez ce que je veux dire. Donc, donne-moi, par exemple, un Bruxellois, donne-moi une fois un verre. Okay, enfin, là, je le fais mal, mais bon, tu vois. Donc, geef mij eens een glas. Le problème, c'est que le eens apparaît comme renforcement. Mais le eens apparaît toujours après le verbe. Donc, si vous voulez vraiment faire l'accent bruxellois pour épater les copains et tout, vous ne dites pas donne-moi un verre une fois, parce que là, on sait que c'est faux. Mais un Bruxellois dira plutôt donne-moi, et il veut renforcer parce qu'il a envie d'avoir son verre, je sais pas. Donne-moi une fois un verre. Voilà. Okay, now in English. Okay, so outline. What are we going to talk about? The University of Liège. Sorry about this introduction. Okay, good to have the attention of everybody. Then the Department of Electrical Engineering, where I work, it's called Institut Montefiore. And then the lab where my lab actually, okay, about 10-ish researchers, Microsys Research Lab. I'll talk today about SPAD cameras. We'll see what a SPAD is, a single photon avalanche diode. We use these type of devices for Lidar and time-of-flight sensors. I'll talk about that. And then I'll talk here about a recent paper, actually. Well, it took some time to realize actually everything, okay, the camera itself. Yeah, and then I'll talk about the paper we published about the camera, and then I'll talk about some things, what worked, what didn't work, like the making of. And then, the proof of the pudding. It's an English expression. It means, if you make a pudding, you want to know if it's good. The proof is you have to eat it. So the demo, yeah, and the mystery guest. There's a mystery guest. Okay, so University of Liège was founded in 1870. Actually, it's Napoleon Bonaparte who said, well, Liège is a big city. It should have a university, and then, the university came by the time that Napoleon was gone, actually. So 1817. Now, previously in Liège, you had the Institut Montefiore. That was one of the first engineering schools, actually, in Belgium, like electrical engineering. And then later on, it actually became part of the university, logical, so everything became the university. But we still say Institut Montefiore. Everybody knows it's Department of Electrical Engineering, and we say Institut Montefiore, or, the students, Montef, like that. More like abbreviations, like you guys know. Now, actually, the campus is outside of Liège. It's outside of the city. This is well, not really the view we have. I guess it's the view we would have if we could see through the trees, but it's like somewhere, in the wooden area. Between Liège and les Ardennes, actually, okay. They used to say, they still do actually, but Liège is la porte des Ardennes. Donc, voilà. Donc, Sartillement, where the university is, it's kind of outside of the city towards the Ardennes. It's a wooded area, actually. Okay, the statue of Georges Montefiore-Lévy, so from Institut Montefiore, and the building itself. Now, Microsys Research Lab. So, in the Department of Electrical Engineering, you have a research lab, the lab where I work. Microsys. So what do? Connected sensor systems like IoT type of, sensor nodes, putting things like measuring, energy harvesting, ultra low power electronic devices and circuit. miniaturized electronic circuits, integrated circuits as well, and also SPAD cameras for the integrated circuit. Okay, the imager itself, but of course the entire electronics around it, which is probably even more interesting. So that's everything I'm going to talk about today. And then we have a clean room. You see a fisheye type of panoramic fisheye photo thing from the clean room. Yeah, with all our equipment. And there we do actually encapsulation of the sensor nodes and stuff and packaging and, you know, making things as small as we can. So most of our projects are European projects and Walloon region projects and so on. So here that's the classic type of, you know, thing we show. So we do design and development, and then modeling, and then making, measuring, and then it doesn't work, you know, or it works, but you know, when you implement stuff. So yeah, so that classic chain actually. But about Liège, did you know that Liège is actually, like my dad says, he's from Liège, he says Liège is the most French city, the Frenchest city, I don't know if you can find la ville la plus française en Belgique. Because on the 14th of July, actually, last week, works city. Why? Well, because of, you know, the end of the war, and then people decided to do that. They still do that today, actually. So on the 14th of July, it's kind of the only city in Belgium where you've got impressive fireworks. Liège is, well, and you've got like streets, and I forget now, street of the Avenue République Française, many things to do with France. Did you know that Liège is known as the Cité Ardente? I thought before that people have the, you know, the sang chaud, the you know that, right? A bit like, you know, getting soupe au lait. It's difficult to translate in English, but, you know, like feisty people, like a bit, you know. But actually it comes from a historic reference where the city was burned and destroyed. So I read that recently. The symbol of Liège. So if you want to go to Liège, you want to meet somebody, you want to look like, you know, like a cosmopolitan guy or girl, you say, let's meet at the Perron. The Perron is kind of the monument, you know. It's here it looks very impressive and big, but I guess it's like Manakepis, you know, which is about this size. It's about, yeah. So, you know, when I was a student or, you know, younger person studying in Brussels, then, you know, we said, like jokingly, please don't take offense, but we said, oh, if you want to find Manakepis, you know, the little peeing boy here, Manakepis, we call it, example, just follow Japanese tourists. And then, you know, from you stand on the old market, you follow the tourists, and, you know, where they stop, and, you know, it's typical. You follow a street and you don't find it, and suddenly a mass of people taking photos of something. Manakepis. Well, the Perron is still bigger, much bigger than Manakepis, but yeah, not like a huge monument, but it stands in the old city center, actually. Very convenient place to meet. If you go to Liège, you have a party, you meet people, you say, let's meet at the Perron. Typical. And so Liège was also ruled by prince bishops in the past. Okay, let's talk about the technical stuff. Okay, so I'm going to talk about SPADs. So SPADs are single photon avalanche diodes. So what are they? They're essentially diodes. We bias them very well above their breakdown voltage. And so the idea is one photon snaps, boom, causes avalanche. And then, you know, the diode avalanches, we detect this, and then we can actually, you know, detect the avalanche. So sudden amount of current flowing, we detect this, it's a digital event, and so boom, the camera triggers, and then we quench the diode, meaning we stop the avalanche current because, you know, it could destroy or consume a lot of current, let's say. So we stop that, we say we quench it, and then we reset the diode and we do another measurement. So how does that work? Well, I'm not a physicist, okay? So many of these things, like I say in French, I'm électricien, I'm not opticien, okay? I'm not a, you know, physicist, but the thing is that happens is you've got the depletion layer, okay? The diode is biased above its breakdown voltage, so it's very metastable. One photon hits charge carrier, creates a pair of an electron hole pair, I mean, that creates like more of them, and then you get avalanche. That's how it works. Now, essentially, this is what happens. Okay, so keep this in mind as we go along. So we bias the diode here. Yeah. So that's the diode curve, but we don't show this. Okay. So in fact, now I show it, but yeah, we go. Yeah, negative voltage, reversely biased. Okay, so we bias the diode here. So very easily, there is an avalanche. Yeah. Hopefully for us, it's caused by a photon, but sometimes it's just caused by temperature or just boom, avalanche, because it's metastable. And sometimes some devices on an imager, well, they always avalanche. Okay. So, and I'll show a couple of them as well. So there is avalanche here, okay, an avalanche event. Let's say because we detected a photon, first thing we do, we quench it. So we reduce the voltage and then we bring it back. So that's quenching, and then reset. Actually, that's so restore bias. So going from here to here, that's actually resetting the diode. And then you might say, that's very easy. Let's do, hard to draw here. Let's do this, you know. And like many things in life, this works, you know, easy things. It works very well, actually. So you've got photon coming in, the diode avalanches, you get a lot of current here, the voltage rises here, which decreases the voltage across the diode. So the diode goes out of avalanche, yeah, it's quenched. And then, you know, the charge carriers that are still there, they can still go through the resistance, you know, go away, I mean, restore. And so you will restore actually the, this initial, what is it, you know, breakdown voltage or whatever. Yeah. Okay. So the thing is, you know, why I talk about this, but this is slow. So we can improve this. And also sometimes we don't want to reset immediately. For instance, if we want to measure or use a SPAD as an imager for time of flight, and we'll talk about this, you typically want to say, oh, okay, you know, I want to like flash Lidar. I want to measure a visual scene, and then, you know, this SPAD avalanches because you're close by. It's measuring time of flight. But, you know, this SPAD is actually seeing this, so it will avalanche. If it will avalanche later. And so you want to actually keep that window open. So you don't want to reset this SPAD so that it fires again, you know, because you're sitting much closer. So you know, you have to actually, there are circuits and applications where you don't want to actually have this constant, you know, quench reset. You want to control this. So I'll talk about that in a schematic. This is just something we tried for a proposal to be cool, and it didn't work. You know, anyway, the ace of spades and the ace of spads, but and then yeah, it looked a bit geeky, I guess. And then yeah. So how do you make a SPAD? Actually, if you want to do it right, it's hard, I guess. Again, I'm not a semiconductor physicist. If you want to do it like a bourrin, then it's pretty easy, I hope, because we're still waiting for the samples to come back and we've just done it. But we've done it in the past and it worked. Like brute force, we designed 5 different SPADs in regular CMOS process without breaking design rules. Well, in fact, trying to. Yeah, and they worked, but they didn't work well. To be honest, we don't care so much about SPADs. So the SPADs that are here, they work. They're not that great because for our work, we focus at the electronics. So for us, the SPAD is a mean to test time of flight and stuff, but we're not like trying to build the best SPAD in the world. Yeah. So easy, actually, in a way that if you want to do it in CMOS, you can do it in an hour. So on the layout, you take an active area. Well, you take a P region, an N region. Now, the only thing you have to watch out for is actually you want the avalanche to be happening here. Yeah, you don't want actually to have breakdown on the side, and so that's why you should actually put these P epi regions. Okay, that's the only thing you have to watch out for. So, also, if you design a SPAD, it looks like a pinhole, une tête d'épingle. See, this is the SPAD. Now, this is the SPAD, and this is the electronics for one SPAD cell. And I'll talk about this later, but it's kind of like a puzzle, you know, like interleaved in each other. But if you look at the active area, ooh, it's this, yeah? Actually, the active area in percent for one SPAD cell, we call that the fill factor. Here, it's about 0.7%. So it's like, you know, like a, oh, you say, what a shame. You know, you get all these photons, but you're only actually active. You're going actually to only measure them, you know, at 0.7% of the total area, so in this pinhole. But why? Well, because let me go back. Because of this, you know, all these areas, it's high voltage. You need to create that high voltage separation. So that will actually give you, you know, the fact that the SPAD is a big device. On top of that, you need to put some electronics around it in order to do counting, in order to do reset, in order to do whatever. Okay, we'll see that. So the SPAD cell is actually much bigger. So because you might say, hey, you know, a CMOS imager here, you know, and resolution, I don't know, but it's very high. Okay, for a SPAD here, the imager it's 64 by 64. So you know, you might say, resolution's not great. That's right, but it's also aimed at different applications. Okay, CMOS imager is for imaging, regular image, SPAD imager, time of flight, intensity, other stuff. Yeah. So a couple of metrics that if you read this or you look this up, a couple of metrics that are a bit like characteristic for SPADs. You know, I've summarized them here. Say photon detection probability. That's something that comes back all the time. So it's probability of breakdown if you have an impinging photon. Usually it's from a few percent up to 50%. If you design SPADs like we do, it's probably below the percent. But yeah, you know, you get many photons as well. So kind of, yeah. Dead time. So once the SPAD avalanches, boom, you need to quench it, reset it. All that time, it takes time. So for our circuit, it's a couple of nanoseconds, but still, you know, if something you should know when you design, yeah, that dead time. So you try to reduce it. Dark count rate. The SPAD is spuriously triggered, typically by thermally generated carriers. So that's that constant. It's very noisy. Oh, you'll see the picture. It's very noisy. If you don't do post-processing, it's an ugly image. Yeah. First of all, resolution is crappy. Secondly, you get like all this noise. Yeah. But okay, this is before processing. You do signal processing after that. After pulsing, so when you get carriers, they're trapped during an avalanche. They get released. Sometimes they generate a second avalanche, and then boom. So other things. Fill factor, I just said this, it's actually the pinhole, you know, with respect to the entire area. For us was about 0.7%. How do you increase, of course, the fill factor? Because, of course, you can, by say you use a SPAD, you use a high power laser, such as this very special device. And then, you know, you can, of course, increase the number of photons that actually are reflected coming back to your camera. So you can use a high power laser. You can also try to increase the fill factor, which in turn will increase the overall photon detection efficiency of the device. Okay, if you look at the device, like the entire thing. So how would you do this? You could, just make the electronics better. Okay, so that's what we try to do in some, you know, works, like trying to make the smallest contrast possible to fit our application. Like trying really to get rid of all the, you know, like any extra transistor, yeah, you try to make it small. 3D stacking. 3D stacking is actually also something we did, is where you put actually, you've got you've got two wafers, so that's a traditional approach. You know, every SPAD cell has this SPAD here, and then the electronics here, and the counter, timing circuit, etc. A 3D approach, actually, I've got a video about this. Something we did actually. This is something a researcher generated from Cadence layout. Actually, looks very cool. Can't stop watching it actually. So yeah, so that's the bottom layer with the electronics, and then so that's the bottom wafer actually. Yeah, and then through a bit of patience, because voila, through a true silicon via. Ooh, the lighting's very bad. Anyway. You guys see this? So it's like a little tower, and on top of that we put the SPAD itself. So you get like this SPAD wafer, and the benefit is you can optimize the SPAD wafer to be like good optically, because usually in life, you know, it's trade-offs. What is good optically is probably very bad for electronics and vice versa. So you get like this SPAD layer, and underneath you got like the electronics layer, wafer, yeah, and then you get true silicon vias connecting the top wafer with the bottom wafer. The disadvantage, yeah, it's very expensive, yeah, so very, very, very expensive. The third one here I won't talk about, it's about silicon photomultipliers. Okay, Lidar and time of flight. So Lidar, you know what that is. It's using light for detection and ranging, light radar with light. One way you can do this is using time of flight. Now, people are very familiar with direct time of flight. There's also indirect time of flight. Direct time of flight, very easy. You shine light, boom. So you've got the speed of light. So you got the stream of photons, boom. A couple of them bounce back. You know, suppose I put this, I synchronize this with the camera. Yeah, you know, it says shoot a laser pulse, and then here it says the clock starts, N1, N2, N3, N4, you know, and then the light comes back, it stops the clock, and then we read out the clock cycles. Very easy, except not very good. I mean, think about this: 300 megahertz clock. That's already fast clock. Yeah, 300 megahertz. We got a wavelength of 1 meter. Okay, so if you take like it's ×2, right? So you detect half a meter. So you've got half a meter of resolution with a clock of 300 megahertz. No problem. You take a clock of 300 gigahertz, which is very easy to do, and then not, and then you have a resolution of 1 millimeter. So okay, 300 gigahertz. That's not going to work. Okay, so what is typically done, and I'll talk about this as well, it's a sort of interpolation. So we're going to interpolate between clock cycles. There's also some clever things you can do, like you know, if you already have an idea about where your target is, you do direct time of flight, perhaps you don't need to start the counter before, you know, the light pulse is almost there. And then you can kind of, or you can use averaging, okay? So you can use techniques, yeah? Indirect time of flight. Indirect time of flight is very precise. Here you're actually going to not send a pulse, you're going to send some type of periodic signal at a much lower frequency, say, I don't know, 100 megahertz, something like that. And you're actually going to receive a signal with kind of, you know, a delay between the phases here. And you are going actually to calculate and do an integration and calculate that phase difference. Yeah. And the advantage is you can do that over many cycles. Actually, you can average this, and you can actually get very precise measurements. That's just an example coming from a paper. I started actually by studying the paper from Nicolas and Charbon. Pardon? Charbon. Wait, pardon. I started actually by reading these papers when I started working on SPADs, because after that, Nicolas published many papers, and I learned many things from that. So here, actually, in that paper, he explains about the authors explain about the indirect time of flight and how you should actually do. And actually, you can prove, and also they show it with measurements, that you actually can get a very high resolution, spatial resolution, actually, by comparing the phases, doing that integration. And it's still a very active research ongoing. We're actually now this is direct time of flight. We step back from direct time of flight. Not that it's not good, but we wanted actually to do very close range imaging now, and so indirect time of flight actually can get higher resolutions with probably more benefits, because there's a couple of like, yeah, what, you know, do you do direct time of flight, indirect time of flight? Well, direct time of flight, I said, you know, you want a picosecond level timestamp for getting a millimeter resolution. So that's very hard. You need clocks like impossible, yeah, very high. Now you can do interpolation, but that's tricky. It's not perfect. It's so you can, but up to a point. So direct time of flight is useful if you want to measure things like from a couple of meters still far away, then definitely direct time of flight. Indirect time of flight use a modulating frequency which is much lower, and you can increase that integration time for increasing the spatial resolution. The problem is that you're going to have a slower acquisition of data. But the thing is, indirect time of flight, while you're looking at phases, right? And so at 100 megahertz, if you get like one wavelength of distance, then you're not going to be able to discriminate between a phase nearby and then multiples of the period. Okay, you guys see what I mean? So for instance, 300 megahertz, you go past 1.5 megahertz, you go farther than 1.5 meters, I mean, and then you see what I mean? And then at a certain point, these things will overlap, and then you won't be able to distinguish. Also, indirect time of flight on board, for instance, cars and something like that, and applications like this, it's difficult because you can also get these multipath reflections. Also, like let's say it's raining or stuff like that. So the phase will be changing because of that. So that makes it more tricky as well. So, two techniques actually which you can study and use in order to use and implement time of flight. Okay, so let's make it concrete. So on board this camera here, inside it all started with an integrated circuit. That's the integrated circuit because it's integrated, as you see here. It's very small. It's a 130 nanometer high voltage CMOS process, yeah, and it has 64 by 64 SPAD cells, which are, kind of interleaved like this into each other, yeah. So, just a couple of things. We have a fill factor of 0.7%, so very small. We have a breakdown voltage of 28 volt. Bon. We've got an active quenching circuit. I'll show you the schematic later. The output signal will give you the event. We use the global clock of 300 megahertz. And I didn't talk about this yet. It's dual mode. So with dual mode, we wanted to see the direct time of flight, so photon timing, but we also wanted to measure the intensity, photon counting. Yeah. So for that, we changed the front-end circuit a little bit. So photon timing, we're actually going to time the time of flight. For photon counting, we're going to say, within that window, how many triggers, yeah, how many events, how many times did the SPAD fire? That gives you something about the intensity. So you can actually do intensity measurement like traditional camera, let's say, and time of flight. So actually, for the same visual scene, like here, you can, with this, it's dual mode, yeah. So you can measure intensity like regular picture. That's why I said smile, you're on camera, and then time of flight. How far are you guys sitting? Yeah. So quenching and reset front end. Okay, a little bit of electronics because it's B branch. Yeah. So okay, so you get the SPAD here. So the idea is it is before avalanche, but biased at a breakdown voltage or above the breakdown voltage, say. The SPAD has not avalanche, so no current is flowing through it. This voltage here is low. This transistor is off. This M4 works as a pull-up. We've got here a high voltage, high voltage, VDD or, higher voltage. Well, voltage in any case sufficient to turn on M2, which keeps this node low, and then, well, that's the loop, yeah? Okay, so suddenly here the photon, this is a photon, the photon hits the SPAD. It doesn't do it like that, but then the SPAD avalanches, and what happens? Okay, so avalanche current flows through the SPAD. It flows through, of course, M2, which is a low resistance. Now, because it flows through M2, this voltage, M2 still has some resistance. Of course, you need to design these things and dimension them accordingly, but this voltage goes up. So M3 turns on. M3 turns on. This voltage goes down. So this voltage is called V feedback. So it goes down. Actually, M2 turns off. And so you get this situation where you stop the avalanche immediately, but then immediately you quench it. You stop the avalanche. And then it's up to you. What do you want to do? Do you want to reset the SPAD or not? Well, if you want to reset the SPAD, it depends. In photon counting mode, for instance. And here, that's actually the entire block here. And I'll go a bit quicker. I'll show it probably here. It's probably better. Okay, so you've got this entire logic block, and it depends on what are the signals that you're going to apply at count, start, disable, all these logic signals that you're going to apply. So basically, if you do photon timing, for instance, you see here the signals that you need to apply. So, start, disable, photon trigger, that's the SPAD triggering because photons come in, so you don't control that. So what happens, for instance, for photon timing, you get, the SPAD is ready, a photon comes in, okay, this voltage, like we said, goes up, yeah, so this becomes high, the feedback goes down, the output here latches, yeah, and then it says, okay, I triggered, okay, I'm high, well, it's high, yeah. For photon counting, you actually want to count the photons, so what you want to do, the photon triggered, you want to wait for a delay, then boom, reset it, and then, again, another event, boom, reset it, okay, and then you want to count that. That's the entire thing here, the logic which is doing that. So it took some time to, I know I'm going a bit quick, but otherwise it's like, electronic numérique, this goes up and this goes down, and that's a NOR gate, in fact. But if you do that, you can actually make a logic diagram, which is very simple. You want to keep it very simple because you don't want to get many components, otherwise fill factor, becomes even smaller, right? So, and then you wanna actually, for photon counting, you wanna set a variable delay as well, because, say the intensity here, you'll see I'll need to tweak and twiddle stuff if the demo works. I don't know. I'll need to, because otherwise you won't see anything, or all the photons, all the SPAD, will have triggered and so on. So you still need to tweak it. So variable delay and so on. Okay, triple integration. Very quickly, triple integration. I said you've got the 300 megahertz clock, you've got the clock cycles, but gives you like a resolution of 50 centimeters, so not very good. We increased it in this camera or better said, up to 2 millimeters by doing analog interpolation. So between each clock cycle, you can essentially, leave out the mathematics, but you can actually essentially have a current source and a capacitance. So you charge up the capacitance, so the voltage increases, and at a certain point you stop it, between clock cycles, and then you can measure the analog voltage and say, it's that voltage, hence it's that time, and then you actually, see, you interpolate between clock cycles. So that's good, but unfortunately, it's not that good. It's good, but it's very susceptible to PVT variations, because if you say current, capacitance, like all these things, I mean, this is great, but then you got some delta on the current. This is not very accurate. The capacitance is, there's systematic offset, so it's like 10% off, and the entire thing here. Okay, so we worked on this, and actually it turns out that if you use 3 of these, it's not me, okay. If you use 3 of these and they're very matched, then you can actually get rid of the PVT variations up to a point. So that's how we obtained the resolution, which, made us happy, like the 2 millimeters. Okay, so camera implementation and experimental validation. So I talked about this chip. I said this before, 2 millimeter depth resolution. So that's the camera. Well, it has undergone a couple of iterations actually, because color changed, new diodes, and still we're still improving it. So that's the board actually inside. So we use that board. That's the imager. And as you see, there's 2 chips. This one I didn't talk about. It's also an imager, but it's expensive to make chips, and then we try to squeeze as much as we can on a chip. So that's another test chip actually. Yeah, so we actually positioned this one here. That's the package, glass lid, the electronics. So first we started testing this, right? Underneath here, you can't see, there's high-speed FPGA board. That's the FPGA board actually that's going to be controlled by the USB cable. So that's why the program is very, very unuser-friendly, because every time you click on something, you're actually sending a command to the FPGA. If you click on the wrong button, then it's done with you in the demo. Okay, the entire thing dies. You have to up, and then do again. So I tested it several times, and hopefully I'll remember to do everything and whatever. Yeah. So it's very don't look at it or You have to synchronize this with the laser, okay? Direct time of flight. So we did this. This is the laser. But we used many lasers, and we're not also optical people, so lasers can be dangerous. We used like help of other people in order to use lasers. But you have to synchronize the laser as well because, well, it's time of flight. So you need to have a very good synchronization between the two. And then we made a little video actually in a dark tunnel with the SPAD, not the camera, but FPGA and PCB. And this is something that always scares my kids because actually you see the tunnel and the depth is I say ooh. Well, anyway, so you see a person walking. They're still little kids, so you see a person walking in a tunnel and doing this, obviously. And as the person goes deeper and deeper into the tunnel, actually the color changes. Yeah, so that indicates the depth. Okay, so the end of the tunnel, it's about 55 meters, is red because red corresponds to 55 meters. The color of the person changes. That's what I meant with very ugly image. Yeah, but it has not been signal processed yet. Okay, it's just the brute frames. I don't remember how many frames here. But with this camera, we can go up to 10,000 frames a second. So, if you get all this data, you could process it very quickly. And how? Well, we're not into image processing as well. So this is the raw data. You can actually, you have many points, a lot of noise as well. But you can also do image processing things to alleviate this. Okay. We did measurements outside as well. Same concept here. Was a big field like 250 meters. We put a high power laser camera board next to it, and then special glasses, everything. It's kind of cool actually. And then for instance here, the number 2, and then this cone here, and then the whiteboard, and then also according to the color. We were actually here in the testing phase, like not really sure how well it would work. So well, this picture I already showed. And what is the future? I don't know. You tell me. But I think what would be interesting, what I would be interested in doing, with sufficient funding and stuff. But what I think would be very promising is actually to do hyperspectral imaging. You could use SPADs, but you could use other imagers. Because again, I said, like CMOS imager. I mean, it's not going to compete for a regular image. This is going to be much better. But if you could, in an ideal application, image the same scene and do it optically, even with separate chips or even interleaved on the same chip or, new technology, you could actually look at a visual scene and see it in a number of different ways. The first way, for instance, would be traditional here. And we didn't do this. I took the images from Google, so it's not our work, but just to illustrate. Classic, scene, yeah? Okay. High dynamic range, because sometimes, when you take a picture in sunlight and some parts are saturated and, like this thing, like having a very high dynamic range, okay, interesting. Depth sensing we could do with the SPADs, yeah? And here, actually event-based, that's something I feel that's going to be more and more important. Event-based means that if nothing moves, for instance, it's like our eyes. Basically, no new information will be recorded. But if something, for instance, moves quickly, like this car, you will see this car lighting up and you won't see the pedestrian walking. You won't see here the pedestrian walking, right? So having events. We did some event-based cameras as well. We worked on this. It's not the same chip, but I'll just show you. This is a fan, okay? So you see here the protection so you don't touch the fan, but you see the fan turning actually. This is event-based, so it's like 2,500 something revolutions per minute, like classic desk fan when it's hot. And you see actually very clearly the blade of the fan which moves. This is the type of imaging that would not be, or would be very hard to do. Put it differently, would be very hard to do. A lot of data if you do it like classically frame-based. If you do it event-based, this was event-based, yeah, then you can get all this information because when nothing moves, then perhaps you don't need all that information. Now you might say, it's perhaps not interesting, but could be very interesting, say, for a robotic application. Yeah, the robot would know the distance, let's say, have a high dynamic range, optical scene, and event-based, everything. Yeah, same image. So because it's actually viewing the same optical scene in different ways, it's called hyperspectral imaging. The fan blades, yeah. The proof of the pudding and the mystery guest. The mystery guest is here. It's here. Okay. So the software. Okay. If you guys can have a kind thought for me, that would be great. Because you have the demo effect and then it doesn't work. Yeah, you know. Well, now I switch on the camera. I plug it in first. Don't make me nervous. Oh, seriously. Well, okay, so there is an LED here. It's blinking, so that's a good sign. Means actually it's booting up. Okay. Well, without jokes, it's connected with USB. Once it's getting recognized, it will do a little sound and the LED will change color. And so I'll know like the computer has recognized it on the USB, which is going to be any time. Click, voila. I start the software. Well, remember guys, this is programming an FPGA. So, yeah, so, okay, so I'm going to connect to the board, configure it, and power the system. So don't ask me why you have to fill in these things, but that's the way the software was designed. Seriously though, it was designed so that we could tweak and try some, you know, as many things as possible. Yeah. So start PLL, configure PLL, enable frequency reconfiguration. I don't know why I'm reading this out loud. Starting this, it's like a checklist, you know. I don't know. I haven't flown a plane yet. Bon, this.
Located in France, it's not possible.
Pardon? What?
You are located in France. Error.
FPGA. He worked in Australia, so. Bon, that's very good. Ta-da! So we don't see it. We don't see anything because the SPADs were not biased, and now remember the photon counting, because I should have said, we're doing photon counting first. Perhaps you saw it here. Photon counting, well, the programming the reference voltages in the FPGA. Bon, etc. configuring PLL, but I enabled the SPADs. This is actually, you know, this delay I was talking about, like, you know, with photon counting. Well, this is actually all these things that you're doing. So for now, we don't see anything. But if we go down, we see the duck. Voila. And then, you know, you can play optically, you know, you can focus a little bit. It's not too bad, actually, like this, yeah? Once I was doing this demo, actually, 2 weeks ago, and somebody said, why does the duck have blue eyes? I was like, is that the only thing you can say about the demo? I was like, why? So I should have brought a cup of. Bon, okay, so it works. Why did I show this? Actually, you see this random, that's the noisy things of the SPAD, okay? That's the SPAD's just dark count rate, yeah? You also see some pixels, and just memorize a few of them, some pixels that are always on. The SPADs, they're kind of not responsive. So there is a way, of course, you can, for instance, and I'll illustrate this very basically, just to see, like, okay, you see the pixels that are always hot. These hot pixels you can actually remove. Well, you take an image here, and then you enable noise reduction, and then actually you see here the image is cleaner. Okay, so there's a couple of things in image processing that you can do and that you can do on Aval. Yeah. So all these things, and we haven't done that. Now, probably the most interesting thing, well, this is photon counting, so just intensity. We can do time of flight as well. Now, time of flight, normally, for doing it accurately, you need a laser. We illustrated this, but it's really a proof of concept, and it doesn't work very well. It works, but you're going to say you're not going to image something at 10 meters with this. We used LEDs on the front. So the LEDs here, this ring, you might have wondered, actually uses to illuminate the scene. And you'll see what I mean. And I should turn on the... Voilà. So this looks like continuous light, so don't look at it. It's like looking at the sun, I guess. Nobody does this, but anyway, disclaimer. So when you look at the LEDs here, it's like continuous light, but it's actually always pulsing. Yeah, so we just don't see this. So if we now look at here, well, that's what I was talking about. So you see here, I think this is the window frame. The black is probably this. This pillar, and then okay. But you see actually if you bring the duck closer or anything closer, it becomes black. So this is something else. Anyway, so if you bring the duck closer, it's getting darker. If you bring it further away, it's getting lighter. So the idea was actually also to color code that depth information. So we started doing this with a color map. Well, essentially, it's the same as it's a black and white one, but it's just, for us, a way still in progress to show, well, like this image, in the tunnel with the, with the color. Yeah. So, but it works, but it doesn't work, let's say, beyond a meter or two. And we have a version with laser diodes. We're looking into that, but laser diodes also, higher optical power, so you have to be more careful. So I guess it's a compromise between bringing something safe to a demo and then getting a very sharp image. So, okay, here, at least you won't get blind. So that's about it. So that was the mystery guest. And that was it. Do you guys have a question? Does somebody have a question about the presentation? Yeah. Enfin, oui, j'ai coupé les LED. Hein, parce que, attends, si j'y arrive. Non, allez-y pour la question. Je ne retrouve pas l'écran.
Déjà, je vous remercie pour votre présentation. C'était très ludique et très agréable à suivre. J'avais une question un petit peu plus sur le côté géométrique et sur les perturbations qu'on peut avoir avec les multiples chemins de lumière qui peuvent arriver sur un élément. Je voulais savoir qu'est-ce que vous faites d'un point de vue layout ou alors même conception de circuit pour réduire ces effets. Est-ce que par exemple, pour la tête d'épingle, il y a différentes géométries qui sont possibles?
Oui, alors il y a des couches spéciales. Par exemple, on peut faire des circuits dans des process intégrés, en fait. Comme par exemple, on a récemment envoyé un circuit en fonderie, en fait, il y a quand même quelques mois, mais chez XFAB. Et là, mais il faut payer plus et il faut que ce soit enfin, bon, il faut acheter ces modèles IP, mais en fait, on peut acheter des modèles de SPAD, en fait. Et là, tout ça a été conçu du point de vue physique, en fait, pour que ça fonctionne bien et pour que ce soit très réceptif et pour que ça puisse capter beaucoup de photos, en fait. Une technique qu'on avait essayé de faire, enfin, sur laquelle on a travaillé, qui marchait très bien aussi, c'est faire des micro-lens. Donc maintenant, ce qu'on fait, c'est faire il y a des micro-lens, donc c'est comme un arrêt, au fait. Et là, typiquement dans notre salle blanche, au fait, on prend le circuit SPAD, on met le arrêt de micro-lens, je ne sais pas comment dire en français dessus, puis on va le positionner, effectivement, on va le mettre dessus. Il faut des spacers, évidemment, hein, comme c'est des lentilles. Donc ça existe, et on peut commander des micro-lens, comme ça. Ce qu'on a voulu faire, nous, c'est faire un processing directement sur le wafer même, c'est-à-dire avec des couches, même faire nos propres lentilles, au fait. Donc c'est un travail qui a commencé, mais de nouveau dans les projets, parfois on commence, c'était intéressant, puis on a poursuivi un petit peu, on n'a pas continué là-dessus. Et ça, c'est par exemple faire des arrêts de micro-lens et les placer dessus, c'est une technique qui est utilisée actuellement dans des produits commerciaux. Point de vue layout, c'est pas ma recherche en fait. Donc pour nous, le SPAD, c'est un moyen, mais les SPAD en soi sont médiocres. L'électronique est bonne, hein. Enfin, l'électronique, je vais dire autrement, l'électronique, on se concentre sur l'électronique. Qu'elle soit bonne ou non, c'est pas à moi de dire ça, mais on se concentre sur l'électronique. Le SPAD, pour nous, c'est un moyen de tester le time of flight. Et si le SPAD est moins responsif, on met un laser qui est un peu plus puissant et tout. On teste ça voilà, c'est des mesures labo, l'électronique, les algorithmes et tout, obtenir les données. Et l'implémentation aussi. Oui? Oui.
Vous avez dit que le rythme avec lequel ça partait des éléments,
Oui.
C'est 2 minutes par seconde?
Jusqu'à 10 000, je pense, de mémoire, oui. Oui.
D'accord. Et les synchronisations, il est fait par chaque frame? Synchronisation pour mesurer la.
Par frame, oui. Pour le time of flight, hein, par exemple.
Et pour cela, il faudrait une synchronisation parfaite. Bon, parfaite. Une bonne synchronisation, on peut dire, entre le circuit et la source de laser.
Ah oui, absolument. Oui, oui, c'est crucial. Oui, oui.
D'accord. Et
Oui.
matériellement, vous faites ça comment avec le circuit, par exemple?
Ah, mais il faut un laser, hein. Donc il faut déjà un laser avec des temps de montée qui sont très très élevés. Et là, c'est vraiment caractériser et tout, et savoir exactement. Oui, ça c'est vraiment du tuning alors. Avec les diodes ici, on n'obtient pas ça parce que le temps de montée déjà, ben, c'est une diode, donc c'est voilà. Oui.
C'est pareil pour le laser, parce qu'on va déclencher même matériellement, ça va prendre
Oui.
un temps de retard.
Ça va prendre un certain temps, mais c'est quand même beaucoup beaucoup plus rapide, hein. Oui, oui, laser, oui, oui. Oui, oui. Donc il y a des high-speed lasers aussi. Là, bon, nous, on utilise des lasers dans le laboratoire qui sont quand même faibles, parce que bon, enfin, faibles de puissance optique pour ne pas avoir trop, on met des lunettes et tout, mais pour ne pas avoir trop de contraintes de sécurité. Dans le laboratoire où je travaillais précédemment, on a utilisé un petit laser. Au fait, on a eu tellement d'ennuis, enfin, avec la sécurité, protection du travail et tout, on a dû construire un interlock avec un relais, on l'avait mis sur une porte, pour faire un truc. Donc, dès que quelqu'un ouvrait la porte, il y a un relais qui se déclenchait, il fallait que ça coupe là. Au final, on était plus occupé à construire un interlock qu'à travailler avec le laser, en fait. Mais, donc, des choses comme ça. Donc, pour éviter ça, au fait, par exemple, les mesures qu'on a faites ici dans le tunnel ou dans le champ, là, à 250 mètres, on a été au-delà même, hein, jusqu'à 750. Ben là, c'était typiquement une équipe au fait, qui maîtrise les lasers. Nous, ce n'était pas notre truc, au fait. Oui. Nous, c'est purement l'électronique et puis enfin, l'implémentation, c'est-à-dire le dispositif, donc la FPGA, l'interaction, enfin, l'interfaçage avec le SPAD, le circuit, enfin, programmation comme j'ai fait ici, au fait. Hein. Oui.
Merci pour la présentation, c'est très intéressant. J'avais une question par rapport aux formes d'ondes utilisées. Donc, vous avez montré soit des pulses, soit un sinus. Est-ce que c'est possible de travailler sur les formes d'ondes pour améliorer justement
Ça, c'est une recherche en cours. En fait, vous avez tout à fait raison. Quand on va regarder sur les indirect time of flight, en fait, les gens essayent de, justement, avec des techniques d'utiliser des ondes différentes et tout, voir des performances différentes. Absolument. Là, j'ai pris le sinus et les pulses comme exemple, mais il y a d'autres types d'ondes.
J'ai une question.
Ah, allez-y.
J'ai une question du coup sur les circuits parce que à chaque fois vous avez un circuit du coup pour une SPAD.
Oui.
Mais est-ce que vous ne pouvez pas du coup avoir un circuit qui va contrôler plusieurs SPAD
Non, enfin, classique, dans une approche classique, non. Parce qu'il faut en fait un compteur par SPAD. Donc il faut pouvoir stocker, compter. Maintenant, est-ce qu'on arriverait à faire un multiplexing? Est-ce qu'on arriverait à... On a essayé de développer des circuits comme ça, et puis on avait commencé quelque chose d'observateur et des circuits. Je pense qu'il y a des manières d'optimiser, oui, personnellement. Sans doute, c'est déjà bien... Enfin, c'est un bon point de départ au fait d'optimiser le circuit électronique en soi. Donc, par exemple, ça, on a travaillé beaucoup sur le compteur pour le faire vraiment le plus petit possible, au fait. Donc, mais alors, après avoir... je pense que ça pourrait être très prometteur. Oui. Je n'ai pas vu dans la littérature encore. Mais, par exemple, pour des silicon photon multipliers, mais ça, le principe est différent. Par exemple, quand j'ai dit ça, je passe, en fait, vous avez peut-être vu en dessous le... J'ai oublié où c'était maintenant. C'était ici. Donc ça, par exemple, c'est différent. Ce n'est pas un imageur, mais c'est en fait comme un photomultiplicateur, mais avec des SPAD. Et donc, on va mettre les SPAD en parallèle, en fait. Et là, c'est vraiment pour une détection de points. Mais là, on utilise beaucoup de SPAD, justement, pour des raisons de précision et tout. Ça ne répond pas vraiment à la question. Mais donc dans des applications comme ça, oui, hein, comme ils sont en parallèle, mais là, on ne fait pas d'imagerie non plus. Donc là, on met l'électronique d'un côté, les SPAD de l'autre. Oui. Mais pour l'imagerie, l'approche classique, ou alors c'est ça, hein, de plus en plus, hein, l'implémentation 3D, mais ça coûte cher, il faut faire l'alignement, il faut faire le packaging, il faut mais de plus en plus, en fait, ça, c'est pas du tout mon domaine, en fait, mais oui, hein. Avec ça, on a un fill factor, ben, vous avez vu la vidéo, hein, c'est quand même, enfin, il n'y a que des SPAD au-dessus, donc on peut vraiment optimiser, en fait.
J'avais une question sur l'accès à la technologie. Par où tu es passé pour
Oui, hein.
fondre le circuit et combien il a coûté plus cher que le canard, le circuit à faire? Dans de grandeur,
Ah, les yeux bleus, c'était en option, donc ça, c'était plus cher. Le circuit, c'était par Silterra, le premier, hein, donc celui-là. C'est une fonderie en Malaisie. C'était encore, enfin, c'était quand je travaillais en Australie. Hein, donc. Là, on avait eu accès par un chercheur qui travaillait pour la défense et qui travaillait avec Silterra aussi et qui avait dit, voilà, j'aimerais bien construire mes SPAD, mais enfin, pour les design rules, ben, à chaque fois, il devait demander une dérogation, en fait, parce que quand on soumet un circuit, on ne prend pas en compte les design rules, mais si ça ne marche pas, enfin, si ça ne fonctionne pas. Donc, à chaque fois, donc, il y avait ça, au fait, il y avait ce problème-là. Mais après, on a fait des SPAD, au fait, dans la même technologie, donc ceci, sans devoir, comment dire, sans devoir, allez, je ne trouve pas le mot en français, en respectant les design rules. Voilà. Mais le prix, je ne sais plus. Ça, oui. Là, on a fait avec XFAB maintenant. Ouais. Là, on attend le circuit. Mais là, c'était par Europractice, XFAB, CMOS, enfin, high voltage, mais je ne dis pas un circuit spécial. Enfin, pas une technologie spéciale. Mais ils ont des SPAD dans cette technologie-là, mais on n'a pas pris cette option-là, on a fait les nôtres. Donc, ouais, enfin, on va recevoir le circuit prochainement, puis les doctorants disent, ah, mais si le SPAD ne marche pas, si ça ne marche pas, et puis, ben, on verra. Alors, ouais. Ça, c'est toujours le risque. Hein, ouais. Mais je pense que ça marchera. En général, ça marche. On a eu ça à Monash, en fait. On a construit les nôtres vraiment comme ça, en fait. Sur un coup de tête, on dit, bon, on va mettre des couches là. Enfin bon, il faut tout de même regarder. Enfin, il faut quand même étudier et voir et quelles couches passer et tout, mettre les isolations nécessaires. Mais c'est possible. Et en fait, les SPAD fonctionnaient, ça ne marche pas très très bien. Il faut éliminer avec un laser puissant, mais voilà.
C'était pour le Bionic Eye que tu avais fait?
Non, ça c'était pour la défense. C'était un projet de l'OTAN en fait. L'idée c'était de mettre des caméras comme ça sur des drones pour voir à travers la fumée, les nuages, tout ça. Et l'idée c'était d'avoir. Non, mais c'est pas inscrit. L'idée c'était d'avoir une caméra format GoPro en fait. Et c'est un peu plus grand qu'un GoPro. Mais pas tellement, hein. Ouais. Un beau boîtier et tout en plus. On a tout fait nous-mêmes, hein, mécanique, tout.
Je pense qu'on va
Si c'est ça, merci beaucoup.
Merci. Pardon?
C'était très intéressant.
Merci.
Jean-Michel sera là toute la semaine. S'il va lui parler, il sera là au barbecue aussi du laboratoire. Vous pouvez lui parler.